Bismillahirrahmanirrahim. My today's lecture is about the solution of partial differential equations. Here we are going to solve the partial differential equation using the Lagrangian method. So for Lagrangian method, we must need a partial differential equation of the type PP plus QQ is equal to R. So small p, we know that small p is the partial derivative of z with respect to x, small q is partial derivative of z with respect to y, and here x, y, z are functions, and capital P, capital Q, and capital R. These three terms are the coefficient of small p, small q, and right hand side. So, and auxiliary equation of this type of differential equation is dx upon p is equal to dy upon q is equal to dz upon r. By this auxiliary equation we can form the solution of such kind of partial differential equation. So the solution can be written as f of u v is equal to 0, and or u is equal to function of v, and also it can be written as pp plus qq is equal to this is the solution of equation pp plus qq is equal to r. So we can write it as in two different forms. So look at the example number 1 to find the solution of differential equation by using Lagrange's method. So according to Lagrange's method, here we have yq minus xp is equal to z. We call it equation number 1. We are going to solve this equation. It means that we are going to find the solution of this equation. This equation can be written as into the general form. What is general form? Capital P into P plus capital Q into Q is equal to R. So we will compare these two equations so that coefficient of P, that would be minus x. So here capital P is minus x, coefficient of Q is capital Q. So the coefficient of Q is y, so that capital Q is equal to y, and R is equal to z. This is function of right at the right hand side. So z is equal to R. Now what we are going to do? We are going to form the partial auxiliary equation. What is the auxiliary equation of by the Lagrangian method? That is dx upon p is equal to dy upon q is equal to dz upon r. So by substituting the value of p, that is dx upon minus x is equal to dy upon y is equal to dz upon z. By from this equation we can divide this equation into two more equations. That would be minus dx upon x is equal to dy upon y, and dy upon y is equal to dz upon z. From this equation, by integrating at left hand side and right hand side, integral of minus x, that would be minus times of ln x, plus integral of y, that would be ln y, plus integration constant ln c1 at the right hand side here. So after the integration, we will get dava y upon y is equal to dava z upon dava z, so that this equation dy upon y is equal to dz upon z can be written as ln of y is equal to ln z plus ln of c2. So this is the equation. Now further, from first equation, the left hand side, that was, we can write it as ln of x is equal to ln of y c1, because these two terms were going to multiply together. So according to the property of log, we can write these two terms in form of product. Now this ln of x minus 1 is equal to ln y of c1 can also be written as 1 upon x, because log will be cancelled out from both sides, and x raised to the power minus 1 can be written as 1 upon x is equal to y times of c1, and from this equation value of c1 would be u, that is u is equal to c1 is equal to xy. Similarly, from the second equation, ln y is equal to ln z c2, and log will be cancelled out, so that we will get y is equal to z c2, and z and c2 will be v, that is y upon z. Now we have got the values of v, u, and v, so that we can write the general solution of the partial differential equation. That would be the solution of partial differential becomes f of uv is equal to f of xy comma y upon z. So this is the required solution of this kind of partial differential equation by using the Lagrange method. Similarly, look at example number 2 here. Now we have example number 2, that is y square p minus x y q is equal to x times z minus 2y. In this equation, coefficient of small p is equal to capital P, that is y square, small q is equal to minus xy, that is q, and rest of all in the right hand side, that would be r. So this time we have clear values of p, q, and r. Now by using the auxiliary equation can be written as dx upon p is equal to dy upon q is equal to dz upon r. So the value of x is what? P is q square, and value of y is x minus xy, and value of z is dz upon x upon z minus 2y. So now dz upon y is equal to dy upon x. By shifting the variable from left hand side to right hand side, so the equation can be written as minus x dx is equal to y dy. Integrate these two terms at left hand side and right hand side, so that the uh, integral of x would be x square upon 2, integral of y, that would be y square upon 2, plus integral constant, that is c1 upon 2. Similarly, we have minus 2 minus z dy plus 2y dz is equal to d of x. And now from this equation here we can obtain the value of c1, so that uh, c1 upon 2 would be written as minus x square upon x square into x square upon 2 minus y square upon 2, so that c1 is equal to x square plus y square and u is equal to x square plus y square. Similarly, second part, that is minus z dy plus 2y and dy is equal to y dz, and 2y dy upon dy plus y dz plus z dy. 2y dy is equal to y d yz, and 2y square upon 2, that would be yz plus c2. Now v is equal to y square minus yz. So the solution, that would be f of uv. F of uv is equal to f of x into y. So what is the value of x? X is x square plus y square, and value of y is y square minus y into z is equal to 0. So this is the required partial differential equation. One more example of partial differential equation, and that is dx upon dy upon x minus y is equal to dy upon dz divided by y minus z. Because we know that integral of 1 upon x, that would be what? Ln of x. So here we will use the definition of log. So here look at this. We have function and derivative. Near we have function, up we have derivative. So downside we have the function, and upside we have the derivative. Now when we have function with derivative, so that we can write ln of the function. So here we have function what? X minus y and derivative of x minus y. So the that can be written as ln of x plus y is equal to ln of y plus z. Wait a moment. So when we have function with derivative, we use this formula, integral of 1 upon x dx becomes ln of x. So we have x minus y is a function, and dx dy is the derivative of this function. Similarly, we have dy minus dz, and similarly we have function y minus z, and derivative is here. So when we have function and derivative, we can take the logarithm. So the integral of this becomes ln of x minus y, and integral of this one will be ln of y minus z. When we have ln with all the terms, we must take the log of the constant. This is the constant of integration, ln c1. So by shifting at right hand side, left hand side, so the equation becomes ln of x minus y minus ln of y minus z is equal to ln c1. Due to the property of log, these two can be written as log of x minus y upon y minus z is equal to ln c1. This log and this log will be cancelled out. Directly c1 will be x minus y upon y minus z. This is the value of c1. Similarly, second factor, that would be dy dz upon y minus z is equal to dx minus dz minus dx upon z minus x. So clearly see that y minus z with derivative dy dz and z minus x with derivative dz and dx. Similarly here, the direct integral of this two term will be ln of y minus z is equal to ln of z minus x plus ln c2. So c2 becomes y minus z upon x minus z. This required solution will be, so that we can write it as according to the definition, f of uv is equal to f of c1 c2 is equal to, this is the value of u and this is the value of v, is equal to 0, which is the required solution. So now in the next lecture I would like to tell you regarding the method of Lagrange multipliers. So see you in the next lecture. Thank you. Bismillah ar-Rahman ar-Rahim. Once again, I would like to discuss with you regarding the method of Lagrange multiplier. This is the method to find the solution of partial differential equation of the Lagrangian type. So, what are the Lagrangian partial differential equation? PP plus QQ is equal to R, and we know that the auxiliary equation of Lagrangian function equation is dx upon P is equal to dy upon Q is equal to dz upon R. So, by using the similar manners, we try to find the solution of such a kind of partial differential equation. But here we need some kind of multipliers. For the multipliers we use the different conditions. For example, sometimes we apply the constants function and for example L, M, and N and auxiliary values of x and y and z. Then this dz upon dp is equal to dy upon dq is equal to dz upon dr can be written as, in case of L, M, N, or when we have multiplier L, M, and N, so that equation becomes L dx plus M dy plus N dz upon LP plus MQ plus NR is, so that this denominator must be equal to 0. And when you are going to find the solution of this differential equation, which is the necessary rule, this denominator must be equal to 0. We say that LPP plus MQ plus NR must be equal to 0, or L dx plus M dy plus N dz is equal to 0. So according to the definition, by using Lagrange multiplier method, we can pursue the solution of partial differential equation. Now if we obtain C1, that is equal to U by L1, M1, N1, it means that by using first set of Lagrange multipliers, and then we use second set of multipliers, we could be write as L2, M2, or N2. So solution from this would be C2, that would be equal to V. So look at the example number 1. Here we are going to find the solution by using the method of Lagrange multiplier, so that our partial differential equation is mz minus ny into p plus nx minus lz into q is equal to ly minus mx. So we are going to find the solution of this differential equation. First of all, here what will be the value of p, q, and r? Capital P is coefficient of small p, that is mz minus ny, and capital Q is the coefficient of rectangle, that is q is equal to q, that is nx minus lz. Q is equal to nx minus lz, and the rest of term, the right hand side would be r, that is ly minus mx. Now the auxiliary equation of this equation would be dx upon p is equal to dy upon q is equal to dz upon r. Choose the multiplier to find the first solution of this kind of differential equation. What are the multipliers? Such that this factor L dx plus M dy plus N dz must be equal to 0. So according to the definition of this Lagrange multiplier, so this equation dz upon p is equal to dy upon q is equal to dz upon r can be written as x dx plus y dy plus y dy plus z dz upon x times of mz minus xy plus y times of nx minus lz plus z times of ly minus mx. After simplification, the numerator can be written as x dx plus y dy plus z dz, and denominator would be mxy minus nxy plus nxy minus lyz plus Lyz minus myz. All the terms will be cancelled out, so that we have 0 in the denominator. So this term will be write as x dx plus y dy plus z dz is upon 0. Now this term will be shifted at the right hand side, left hand side, and when they will multiply at the left hand side, here we have three factors. All these three factors will be 0 when we multiply by 0. So that x dx plus y dy plus z dz is equal to 0. Now to find the solution of this one, we have to integrate. When we will integrate x with respect to x, that would be x square upon 2. But sorry, we are integrating partially, so that integral of x with respect to x would be x square upon 2. Integral of y with respect to y, that would be y square upon 2. And integral of z with respect to z will be z square upon 2. So that the constant will also c1 upon 2, taking common from the entire term and 2 cancel out, so that the first solution c1 is equal to x square plus y square plus z square by using the first multiplier. Now we have to choose another set of multiplier, because this is our c1. Now we are going to find the solution of c2. This c1 is also known as, you can call it u. Now we are going to find v, that is c2. For seconds solution, we choose the multiplier, that's r. Lmn is equal to Lmn. So this time we are choosing the multiplier Lmn, so that for instance capital P, capital Q and capital R, we must substitute Lmn. Now after using this multiplier, so the auxiliary equation becomes dx upon p is equal to dy upon q is equal to dz upon r is equal to L dx plus m dy plus n dz divided by L time mz minus ny plus n time nz nx minus ly plus n time ly minus mx. So after simplification, Lmz minus Lny mnx mlz and ly or mx, this term will be cancelled out together, so that denominator will be 0. So the remaining term would be L dx plus m dy plus n dz upon 0 when this multiply at left hand side. So left hand side's all term will be 0, so that this equation can be written as L dx plus m dy plus n dz is equal to 0. After the integration, you will get the integral of dx will be the x, because L is the constant, so that will be Lx plus my plus nz is equal to c2. So this is the value of c2. Now the solution of the differential equation can be written as f of c1 c2 is equal to f of uv is equal to f of value of u, f of value of v is equal to 0. This is the required solution of partial differential equation by using the method of Lagrange multiplier. Now we have another example. Lagrange multiplier is very common and popular method to find the solution of such kind of equations, which are known as Lagrange's partial differential equation. Now look at the example number 2. In example number 2, we have x into z square minus y square p plus y x square minus z square into q is equal to z times y square minus x square. From here we will equate the value of capital P, capital Q, capital R. That would be P is equal to x times z square minus y square, Q is equal to y times x square z square, or R is equal to z times y square minus x square. So how to pursue the solution? Now the auxiliary equation of the given differential equation becomes dx upon p plus dy upon q plus dz upon r is equal to lp plus nq plus nz upon lp plus ldx plus ndy plus ndz upon LP plus NQ plus NR, so that after substitution this can be written as x dx plus y dy plus z dz upon x square z square y square plus y square z square x square minus z square plus z square y square minus z square. So there will be dx upon p is equal to dy upon q is equal to dz upon r, right? And at the right hand side we can write it as x square z square plus x square y square minus x square y square plus x square y square minus y square z square plus y square z square minus x square z square. So after that this may be written as x dx plus y dy plus z dz is equal to 0. So that denominator will be 0 and this will be shifted at the right hand side. So at the right hand side entire term will be 0. Only we have three terms at the left hand side, we must be integrate. So the integral of x square upon 2, that will be x dx, y dy, z dz. X square upon 2 from this, y square upon 2 from this, z square upon 2 from this, and taking common 2 from the entire term, so that we can write it as 1 upon x dx, 1 upon y dy, plus 1 upon z dz. So look at this. 0 is equal to 1 upon x dx plus 1 upon y dy plus 1 upon z dz. So after integration, this can be written as ln x plus ln y plus ln z. Ln y zx is equal to ln c2. So c2 is equal to x y z. This is the required solution of the given differential equation. Now what we this is another example of partial differential equation. Here we have this differential equation is little special type of differential equation. So here look at this, x square minus y square minus z square into p plus 2xyq is equal to 2xz. So taking common, equating the values of capital P, Q, R from this equation, that would be p is equal to x square minus y square minus z square, and q would be 2xy, and r is equal to 2x into z. Now the auxiliary equation of this differential equation can be written as dx upon p is equal to dy upon q dz upon r, that is dx upon x square minus y square minus z square is equal to dy upon 2xy is equal to dz upon 2xz. Now from these factors, we can take two terms which can be suitable to find the first solution. So from these two factors, taking these two ending factors, so that we can write here from last two terms, we can write dy upon 2xy is equal to dz upon 2x. 2x will be cancelled out, so this equation will be dy upon y is equal to dz upon z. So this is variable separable differential equation, so that we can directly integrate. That would be integral of 1 upon y, that is ln y, integral of 1 upon z would be ln z, and when we have log with all the terms, so that we use the log with constant, and this will be shift at left hand side. So according to the property of log, ln a minus ln b can be written as a upon ln a upon b, and log will be cancelled out, so that c1 would be y upon z. This is our first solution. For the second solution, we can write it the equation, use the multiplier x y z. So after using the multiplier, so this equation can be written as L dx m dy n dz. Similarly, np mq nr is equal to dx upon p dy upon q dz upon r. So dx x dx y dy dz will remain as it is, and in the denominator x is common, and similarly this x will be cancelled out from the last factor, that is dz upon 2xz. So this will be cancelled out, so the remaining term is now x dx plus y dy plus z dz upon x square plus y square plus z square is equal to dz upon 2z. Now we have derivative. After the cancellation, this 2 will also be cancelled out when we will multiply and divide by 2, and at the numerator we can write it as 2x dx, 2y dy, 2z dz, and 2x square y square z square. This 2 will be cancelled out. Now we have complete derivative of x square y square z square, and you know that the derivative of x square is 2x dx, derivative of y is 2y dy, and derivative of z is 2z dz. So we have complete function with derivative, and that you know that the integral of 1 upon x would be ln x, so that integral of x square y square will be ln of this function, yani x square plus y square plus z square. Similarly, integral of 1 upon z, that would be ln of z plus ln of c2. Now we will shift at left hand side according to the property of log. This will be into the division. Ln of a minus ln b would be ln a upon b. So ln will be cancelled out. So c2 is equal to x square plus y square plus z square upon z. This is our required solution, which can be written as f of c1 c2 or f of uv or u is equal to f of v. There are several ways to write the solution of such kind of differential equations. So I am writing f of c1 c2 is equal to f of, this is the value of c1, this is the value of c2. So this is the solution of this differential equation. Now we have another example. In this example we have the problem x square p plus y square q is equal to xy into z. So here what is the value of capital P is x square, capital Q y square, capital R is x y into z. Now auxiliary equation according to the definition, dx upon P is equal to dy upon Q, dz upon R is equal to dx upon x square, dy upon y square, dz upon x plus y into z. Now from this one we can equate the first two terms, because these two terms are integrable, so that we can write here from first two terms dx upon x square is equal to dy upon y square. Now integrating on both sides, integral of 1 upon x square will be minus 1 upon x, integral of 1 upon y square will be minus 1 upon y, and plus integration constant c1. So by taking the LCM we can equate the value of c1, that is c1 is equal to x minus y upon x into y. So this is our first solution. Now we are going to pursue the second solution. According to the auxiliary equation, we can write auxiliary equation dx upon x square is equal to dy upon y square is equal to dz upon z time x plus y. This x square can be written as x into x and y square y into y. Why? Because we are going to predict the value of Lagrange multiplier. So 1x and 1y from these two terms will be shifted into the numerator, so that this will be written as dx upon x, this dy upon y into upon y, and this dz upon z times of x plus y, dz upon z upon x plus y. Now we are taking Lagrange multiplier here. What are the Lagrange multiplier? 1 upon x, 1 upon y, 1 upon z are the Lagrange multiplier. Here we are using the value of L, M, N, 1 upon x, 1 upon y, 1 upon z, so that this will be written as, or you can say that multiply and divide by x, y, z. So when you are multiply and divide by x, y, z, so the left hand side here we have x, that would be x into x, 1 upon x square, 1 upon y, y square, 1 upon z, x, y, z. So what happened? This x will be cancelled out, this y will be cancelled out, and this z will be cancelled out. So the remaining term will be only 1x plus y minus x minus y. So 1 upon x dx plus 1 upon y dy minus 1 upon z dz, right, upon x plus y minus x plus y is equal to dx upon p is equal to dy upon q dz upon r. So 1 upon x dx, 1 upon y dy minus 1 upon z dz upon 0. So when this 0 will multiply these three terms, all the terms will be 0. Only we have 1 upon x dx, 1 upon y dy, 1 upon z dz is equal to 0. Now integrate, so that integral of 1 upon x will be the ln x, integral of 1 upon y will be the ln y, 1 upon z will be the ln z is equal to ln c2. This is our constant of integration. Now these two terms are getting adding, so that according to the property of log, ln a plus b minus c can be written as ln of ab upon c. Log will be cancelled out, so c2 is equal to x into y upon z. This is our second solution. So this can be the required solution can be written as f of c1 c2 is equal to f of uv is equal to f of x minus y upon xy into xy upon z is equal to 0. Now one more example, example number 5, y plus z p minus x plus z q is equal to x minus y. Here p is equal to y plus z, q is equal to minus x plus z, r is equal to x minus y. Now the auxiliary equation of this equation, dx upon y plus z minus dy upon minus x plus z dz upon x minus y. First we are using multiplier 1 1 1. What happened? By using this multiplier, all the terms will be provided the 0 in the denominator. So look at this, what happened? and we are using this multiplier, so that this equation dz upon y plus z dx upon y plus z dy upon minus x minus z dz upon x minus y can be written as dx plus dy plus dz upon y plus z minus x minus z plus x minus y. This is L dx m dy, because we have L m n is 1 1 1, so this all the terms will be cancelled out, so the remaining term would be dx plus dy plus dz upon 0. This 0 will be multiplied at the left hand side to all the terms will be 0, so the remaining term becomes dx plus dy plus dz is equal to 0. From this equation, after the integration, we can obtain our first solution. So the solution of dx will be x, integral of dx will be x, integral of dy will be y, dz will be z. So thus after integration we obtain x plus y plus z is equal to c1. This is our first solution. Now we are using the multiplier for the second solution. These are x, y and minus z. So look at this, auxiliary equation become dx upon y plus z, dy upon minus x minus z, dz upon x minus y is equal to x dx y dy minus z dz, and the denominator x times y plus z minus y times x plus z, z times x minus y. So after simplification, after multiplication, in the denominator xy xz minus xy minus yz minus zx plus yz, all the terms will be cancelled out. So dz upon y plus z dy upon minus x minus z dz upon x minus y will be equal to 0, because in the denominator we have 0. So this term, this term will be equate from the 0. So x dx y dy minus z dz is equal to 0. After the integration, the integral of x will be x square upon 2, y will be the y square upon 2, and z square upon 2 is equal to constant c2 upon 2. From here, taking common 1 upon 2 and 1 upon 2, 1 upon 2 will be cancelled out. So the C2 is equal to x square plus y square minus z square. This is our second solution, and the required solution can be written as f of C1 C2 is equal to uv is equal to f of C1 C2. One thing before ending my lecture, I would like to explain you that when you are going to choose the value of multiplier, you have to must think about the values of the multiplier, taking the values of p, q and r in the rough work. When you add and subtract, these values must be provided 0 after multiplication by some values. For example, when you are choosing the values L, M and N, and you already have the value of P, Q and R, you already have the values of capital P, Q and R. So when you apply this factor LP plus MQ plus NR is equal to 0. Why? Because you must choose the value of LMN. So you must be choose the value of LMN such that these equations provided 0. So that is why we choose the different values of Lagrange multiplier. By keeping in mind the definition, we must have the 0, because we want to terminate the rest of unwanted terms, so that in the denominator we must require the 0 by substituting the value of L, M, N, so that we must choose such values which provide this factor 0. So you must keep in mind. So thank you for your watching my lecture. I would like to request you, please, if you like my effort, like and subscribe my channel. I would be really thankful to you. Assalamu alaikum.